Okay, and so we move on to section 15.5, the last final section of graph theory. Well, actually, the last section of the textbook. So this is it, graph theory for weighted graphs. Our third section on weighted graphs. If you recall, we've had section 15.3, which was on minimum spanning trees. Section 15.4 on the Chinese postman problem. And now section 15.5 on the traveling salesman problem. And let's think about it. 15.4, a postman has routes that he has to travel along, or she has to travel along, and we want to minimize the time, for example, spent or the distance traveled. So we want the path of minimum weight where we consider the edges as being the primary variable of concern. But for the traveling postman, the traveling salesman, he has to go, or she has to go to different cities, for example, or different houses, and now it's the vertices that are the primary issue. We want to make sure we get to each vertex using the shortest or minimum weighted path. So now we're looking at it from a different type of problem where it's not the edges, but rather it's the vertices. And to do this, we're going to have a new table. We have an adjacency table and a weighted table. And now we're going to have another weighted table, which is different than the original weighted table. It's a way of looking at it a little differently. And this is called definition. This is called a table of least weights or least distances. A table of least weights or least distances shows the length of the shortest route between each pair of vertices. Each pair of vertices. So a normal weighted table gives you the weight of the direct route between each pair. Here to here, this is the one that connects them. What's the weight? A table of least weights says, okay, well, I can get from here to here actually via this other path, and this other path might be less weight than the direct path. That's the weight that we're going to write down. So each pair of vertices in a graph. So let's just do first a very quick example just to demonstrate this. Very simple graph. A, B, C, and D, 4 points, 4 vertices. Additional cross a path that connects B and C directly. And that one's 110, 45, 50, 60, and 70. So what we're going to do here is actually do 2 tables. This is the original table. This is the weighted table. Let's, okay. So we have A, B, C, D, A, B, C, and D. This is the original weighted table. So A to A distance 0. There's no loops here. So those are all zeros. A to B directly is 50 in either direction. A to C is 45 in either direction. A to D, there is no A to D. So this wouldn't even appear on the original graph. There's no connection from A to D. B to C is 110 in either direction. B to D is 70 in either direction, and C to D is 60 in either direction. So, and I guess, to be honest, if we're going to do those dashes for the ones that don't exist, we should do the same for those because there's no connection from A to A. So, or you could even just leave them blank. And this gives the connections between different pairs of vertices. So now let's do another one. And this one is going to be the table of least weights. So A, B, C, D, A, B, C, and D. Okay, so this one, A to A, the least weights to get there is 0. And you can get there by staying there. So this is, remember, this graph is not connections. There's no connection from A to A, like there wasn't before in the last table, which is where we left it blank. Here, the least weight from A to A is 0 because you don't have to move. You can stay there. If you think of a Markov chain as a sequence of states, you can stay in the same state and not make any movement. So distance from A to A would be 0. A to B, it's clearly, just by inspection of the graph, is clearly 50. A to C, clearly 45. A to D, well, there's 2 basic routes from A to D. I can either go the left route, which has a weight of 105, or the right route, which has a weight of 120. Any other route would have to cross 110 or do repeats, so clearly 105 by inspection. Of course, we have symmetry, so let's fill those in here. And these are zeros, we can fill them in. B and C. Well, the direct route from B to C is 110, or I can go down, which is 130, or I can go up, which is 95. So the shortest route from B to C in either direction will be 95. B to D, directly 70, and clearly just by inspection, nothing can beat that. And then finally, C to D, we have a direct route of 60, and by inspection, nothing can beat that. So this is the table of least weights. It's the shortest route between any two. That's going to be huge for this section. Just like last section, the first step was computing the degree of each vertex to determine whether they're all even, 2 of them are odd, 4 of them were odd, or in theory, other situations. Here, the first step is the table of least weights. Notice, by the way, that the table of least weights satisfies what's called the triangle inequality. The triangle inequality is an extremely important result in mathematics. In fact, it's one of the basic axioms, basic assumptions of a whole branch of mathematics called metric space theory. And it says that if you have a direct route between 2 points, it has to be shorter than any side route which moves through another point. So if I have points x, y, and z, I can say the distance from x to z must be less than or equal to the distance from x to y plus the distance from y to z. Now, how does that relate to graphs? Well, we can see here in this particular graph, for example, that the distance from B to C, which is 110, is greater than the distance from B to D plus the distance from D to C. So this original graph fails the triangle inequality. It does not satisfy the triangle inequality. Whereas the table of least weights, if I do the least weight, right? If I put in numbers here for the original, so I'm going to put in here for original. The distance from B to C in the original is 110. It's greater than the distance from B to D, which is 70, plus the distance from D to C, which is 60. But the new one, the table of least weights, the distance from B to C least weight-wise is 95. The distance from B to D least weight-wise is 70. And the distance from D to C least weight-wise is 60 again. And now it does satisfy the triangle inequality. So tables of least weights do, and original ones may or may not. In this case, it does not. Okay, so with that under our belt, we have some more definitions. Remember, we had a whole list We had trails and cycles and walks and loops. And what are some of the other ones we had? Tree and circuit. So now we have a new one. A path is a walk which does not repeat any vertices. So we know that a trail was a path that does not, a trail was a walk that does not repeat any edges. A path is a walk which does not repeat any vertices. And note a cycle is a path, because a cycle also by definition does not repeat any, well, except for the endpoints. So I guess a cycle is a path. Well, let's be a little more rigorous and do it words that the book uses. A cycle is a walk that begins and ends at the same vertex, begins and ends at the same vertex, but otherwise does not pass through any vertex more than once. So another definition, a Hamiltonian path. So if you recall last time we had an Eulerian trail, a Hamiltonian path or cycle, a Hamiltonian path or cycle. Well, if we think about it, this is a name. The name Hamilton is a very famous physicist and mathematician. The Hamiltonian is the central object in advanced physics. But what is a Hamiltonian path or cycle? It's a path or cycle which passes through all the vertices, which passes through all vertices of a graph, much like an Eulerian trail or circuit passes through all edges of a graph. A Hamiltonian path or cycle, oops, I left out a few words there. Is a path or cycle which passes through all vertices of a graph. And one last definition, a complete graph has every two vertices directly connected. So for an example, here's an example of a complete graph. Let's draw the one with 5 vertices. So here is a 5 vertex graph. If I want to have a complete one, then the vertex A has to go and connect directly to B, C, D, and E. B has to go from A, C, E, and D. C, A, B, E, and D. D, A, B, C, and E, E, A, B, C, and D. So this would be a complete graph of 5 vertices. Okay. So now, what is the classical traveling salesman problem? the classical traveling salesman problem is to find the Hamiltonian cycle of least weight in a complete weighted graph. That's the classical traveling salesman problem. Classical traveling salesman problem. The practical traveling salesman problem, the practical TSP, is to find the walk of least weight passing through every vertex of a graph, starting and finishing at the same vertex. So what makes the practical one different than the classical one is that we do not require completeness for the practical traveling salesman problem. The classical one is it has to be complete. The practical one is it does not. Notice that the wording in the book, a walk that passes through each vertex, starting and finishing at the same vertex, is different than finding the Hamiltonian cycle, because who's to say that there is a Hamiltonian cycle? How do I know that I can do so without repeats? Maybe I can, maybe I can't. So the practical one relaxes that condition. I don't need to be complete, doesn't have to be Hamiltonian. It just has to hit each vertex, starting and stopping at the same one without any repeats. And the problem is, unlike some of the others, is that the minimum spanning tree, we had two algorithms, Kruskal's algorithm and Prim's algorithm for finding the minimum spanning tree, no problem. For the Chinese postman problem, we had different scenarios depending on how many odd degree vertices there were. But essentially, again, we had an approach of doing so. The traveling salesman problem does not have a systematic way of finding the answer. So the best we can do without examining every single possibility, of course, if you want to do that, you'll find the answer, no questions asked, but we don't always have the time for that, especially if there's thousands upon thousands of vertices. So what we can do is we can find upper and lower bounds and say, okay, it's got to be less than this, it's got to be more than this, it's somewhere in here, that's the best I can do. So what we're going to be focusing on in this section is finding upper and lower bounds for the final answer. So the first half of the section is finding upper bounds, and that's going to lead to exercise 15I. And then the second half of the section is finding lower bounds, and that's going to lead to section 15J. So let's start with finding an upper bound. Finding an upper bound. Okay. And this one actually does have an algorithm. And let's demonstrate that with the following example. So here's A, here's B, here's C, here's D, here's E, and that completes that. We have F here, coming from A, going to B, going to C, F down to G, G goes to C, G goes to D, G goes to E, and it looks like that is the graph. And let's throw in the weights, 11, 11, 6, 5, 10, 9, 12, 5, 10, 13, and 21. So how do I find an upper bound? Well, one way of finding an upper bound is just pick any order of vertices that, that connect, that hits every vertex. For example, I'll do the one the book does. A goes to B, goes to F, goes to C, goes to D, goes to G, goes to E, and back to A. That hits every vertex. A to B is 11. B to F is 10, 21. 21 to C, 33. Oh, I left this one out, 33. And 7 is 40. 53, 59, 70. All right, so this one is 70. Is that the best one? I don't know, but I can tell you one thing. Whatever the best one is, it can't be more than 70 because 70 is better than that. So worst case scenario, I can do it with a weight of 70. What are these? We're talking about hours here. The graph shows the connections between 7 cities. A driver needs to make deliveries to all these cities, beginning and ending in city A. The weights are the driving times between the cities measured in hours. So I know for a fact that I can do it in 70 hours. But can I do that in less time? And the answer is, well, let's check. So is this the best upper bound? Is this the best? Yeah, is this the best upper bound? Can I find a better upper bound? And the answer is, well, we can use the nearest neighbor algorithm. So let's check using the nearest neighbor algorithm. What is the nearest neighbor algorithm? It's very straightforward. The first thing we're going to do is we're going to create a table of least distances. Now, this is unfortunately the most time-consuming part of this. But on a test, on a homework, on the IB exam, if this question is asked, the time provided will include time to draw or to write out this table. So A, B, C, D, A, B, C, D, E, F, and G. A, B, C, D, E, F, and G. Okay, so let's take a look. Obviously, there's no loops here, so every one to itself is going to be 0. A to B, just by inspection, is clearly 11, symmetry. A to C. Well, there's a few roots from A to C. If I go A, B, C, that's 20. But if I go A, F, C, that's 17. In my inspection, I don't really see anything better than 17. A to D. So let's see, we already have 17. If I go straight down, that's 24. But if I go A, F, G, D, that's 23. And that looks like that's the least for AD. AE directly 11. AF is clearly 5. And AG is 10. Again, these are all by inspection. BC, clearly 9. BD is 16. BE. Well, let's see. If I go through A, it's 22. If I go that way, it's 10, 5, and 6 is 21. I'm pretty sure 21 is the best. And then BF, direct root 10. And then BG is going to be 15. CD, we got a 7. That's going to be that. And then CE, it looks like 10 and 6 is 16. And then CF, I have a direct root of 12. And then CG, oh, I have a direct root of 10. DE, I have a direct root of 13. That seems to beat everything. I think DE. Oh, I'm sorry, I was looking at the wrong one. That was DG. I might as well fill that in. DG is 13. DE, I have a direct root of 21, but I also have a 13 and 6. And I think 13 and 6 for 19 is going to be the best. DF, 13 and 5 is 18. And that beats 19. So it looks like 18 is going to be the best for that one. EF, 6. That's going to beat 6. And I don't think anything's going to look. Oh, I was looking at the wrong one. Whoops. So they will beat 6. Because I was looking at the wrong one. You got to be very careful here. It's so easy to make mistakes. EG is 6. EF is 11. And then FG is clearly 5. Okay, so step 1 is create a table of least distances or weights showing the shortest route between any two vertices, right? Step 1, create table of least weights. And then what is the nearest neighbor algorithm? Well, choose any starting vertex. Now, in our example, we have no choice. They said start with A. Okay, so we're going to start with A. Now, what we're going to do is we're going to cross out the column of A because we've already used it. And then we're going to look in the row of A and we're going to find the vertex that has the shortest distance away, which is F. So A is going to go to F. Now we're going to cross out F. And then what we're going to do, because now we're standing at F, is we're going to look at the row of F and we see the closest, the nearest neighbor to F is G. So we have F, A, F, G. And then we're going to cross out G. And if I look at G, the nearest neighbor is E, A, F, G, E. Cross out E. And I see that if I look at E, the nearest neighbor is C. Cross out C. And if I look at C, the nearest neighbor is D. Cross out D. And the nearest neighbor is B. And of course, now we're done. And then we have to get back to A. Now, these vertices might not be corrected. So let's fill in the blanks if they exist. A is directly connected to F, which is directly connected to G, which is directly connected to E, which is not directly connected to C. There is the need to throw in G in between. Once I'm in C, I can go directly to D. Once I'm in D, I cannot go directly to B. So if I want to get to B, which color do I think this one? From D to B, 16 as C, and then B, and then B, I can get directly to A and the shortest route. So let's calculate this number and see what it is. A to F is 5, F to G is 5, G to E is 6, E to G is 6, G to C is 10, C to D is 7, D to C is 7, C to B is 9, and then we have 11. 5, 10, 16, 22, 32, 39, 46, 55, and this becomes 66. And we see that 66 is in fact less than 70, and 66 is the upper bound for the best, for the minimum weight using the nearest neighbor algorithm, which, by the way, is likely to work. And I would have to imagine would work for any IB test question, but in real life does not necessarily give you the best answer. It's just what you get as an upper bound from this algorithm. So again, step 1 is to create the table And step 2 is to follow the process that we just went through, starting whatever vertex you begin with, finding the smallest weight in that row, crossing out column, go to that row, cross out column, go to that row, cross out column, go to that row, and so on. And of course, once you get to the end, getting back to the beginning as fast as possible. So question A was to, this example that's on page 723, question A was to make the table. Question B was use the nearest neighbor algorithm beginning at town A to find an upper bound for the length of the driver's journey. And C, if the driver were to follow this route, which towns would he pass through more than once? And I already included that in my answer. We see that he would pass through G and C more than once. Okay, well, that is the end of this section. So let's jump into exercise 15I. And we'll have some problems. It says, keep your answers to this exercise available as they will be needed for exercise 15J. So question 1, for each of the following graphs, construct a table of least weights. That's part A. Then B, hence, use the nearest neighbor algorithm to find a Hamiltonian cycle around the complete graph, and also the route that will be needed taken around the original graph. State the total, by the way, just to clarify, the original graph does not have to be complete because not every vertex is connected, but the table of least weights makes a complete graph. If you would actually graph the table of least weights, look at the table. Every 2 vertices are connected to each other because there's a way of getting there. So the table of least weights is creating a complete graph. So again, part B, hence use the nearest neighbor to find a Hamiltonian cycle around the complete graph, and also the route that will need to be taken around the original graph. That's what we did here. This was a Hamiltonian cycle. Nothing was repeated except for the original point and the final point. And then this was the path in the original graph that does have repeats. State the total weight of the route, basically what we just did. If more than one route is possible, give the upper bound for both routes and then select the better upper bounds. Okay, so we have 4 parts here. So let's do A first. Here's a graph. We have A, we have B, we have C, we have D, we also have E, which is connected to D, and E goes to A, and A goes to D, and D goes to B, and that's it. And then we have weights. We have 9, 7, 6, 4, 8, 9, 3, and 10. Okay, so the first thing we're going to do is we are going to make our table of least weights. We have A, B, C, D, and E. And again, you should be doing this yourself before just looking at my answers. So those are the easy ones. A to B directly is 9. I don't see anything beating that. A to C. It looks like if I go along the top route, it's 9 and 7 is 16. If I go along the bottom route, I get 19. But if I go right through the middle, I get 14. So it looks like A to C is 14. A to D is directly 8. And A to E is 10. That's 11, 10. Okay, A to E is 10. Meanwhile, B to C is a direct 7. B to D is a direct 4. And B to E can't beat 7, 4 and 3. C and D, it's like 6 is very nice. C and E, I have 2 different ways of getting there with 9. And then finally, DE is clearly 3. Okay, so that's the table of least weights. And now it says use the nearest neighbor algorithm to find a Hamiltonian cycle around the complete graph, and also the route that will need to be taken around the original graph. Doesn't tell us where to start, which means we're going to try 5 different possibilities. Possibility 1, I started A. So I'm going to cross these out. And I look at the row for A, and I go to D with an 8. Cross out D's. D to E, which is 3. Cross those out. Now I'm at E, which goes to B with 7. Cross those out. And then B obviously goes to C with 7. And then I return back to A. So A to D is 8. I can do that directly. D to E is also directly. That's 3. E to B is not direct. So I need to throw in from E to B. I got to go back through D to get that B. So that means that it's going to be, well, I can write 7 for the EB connection, even though it's broken down to 3 and 4. And then B and C is 7 again. And then how do I get from C to A? Back through D. And I know C to A from my table of least squares is going to be 14. So this gives me a total of 10, 18, 25, 39. So if I start at A, then it's going to be 39. What if instead of starting at A, I started at B? Let's see what happens here if I start at B. So that's option number 1. If I start at B, so I'm going to cross out, you know what, let's not use orange. It's, let's do blue. Okay, so if I start at B, and then I cross out, I'm going to use these easier to erase afterwards. I cross out the B's. So I look at B, B can go to D, and that's direct. And then D can go to E, and that's direct. And then E can go to C, and then that's direct. And then C can go to A, and then A has to return to B. Okay, so let's take a look. So B to D, it's 4. D to E is 3. E to C is 9. C to A is 14. If I go through D again, and then A to B is 9. So 4 plus 3 is 7, plus 9 is 16. 16 plus 14 is 30. This gives me 39 as well. All right, that gives me 39. So 2 different ways so far, starting at A or starting at B, both give me a 39. I wonder if they all give me 39. I don't think they would. Let's try this one. Okay, so let's try starting at C. I cross out all the C's, and I look at row C, can go to D, cross out D, and I go to E, cross out E, and I can go to B, cross out B, and I can go to A, which then returns me to C. So let's take a look. C to D, that's directly connected at 6. And D to E is 3. E to B, I can't do, but I can throw in a D, and that's E to B is 7. And the B to A is 9. And then A to C, I already know is 14, even though I have to pass through D again. So 16, 25, 39 again. You know, if we always get the same number, no matter where we start, that would certainly save us a lot of time. But I don't see why it has to be that way. Let's do brown. Let's see, does it say anywhere in the section that you always get the same thing? Doesn't say anything about always getting the same thing. But you know what? No, I'm not sure. If we always get the same thing, I'll certainly trust it, but I don't know why that has to be. I have to think about that. Meanwhile, D goes to E. E goes to B. B goes to C. C goes to A, which then returns to D. So D to E is 3. E to B, which passes through D, is 7. B to C is 7. C to A, which passes through D, is 14. And then A to D is 8. 10, 17, 30, 39 again. Well, remember, the question says if more than one root is possible, give the upper bound for both roots and select. No, so okay, so far they're all 39. And then let's just do one last example, starting at E. So let's erase these. That might be a good question for your IA if you want to do it on the traveling salesman problem, whether or not it makes no difference where you start. Anyways, of course, it has to be more than just that, but it's a good starting point. So let's take a look. If I do E, E goes to D, D goes to C, C goes to B, C goes to B, and then B, of course, goes to A, which then has to return to E. So E to D is 3, D to C is 6, C to B is 7, B to A is 9, A to E was 10. Well, hold on there, buddy. E to D is 3, D to C is 6. Well, actually, you know what? This is B to A. Actually, it's the numbers that are, it's the numbers that you're circled in the table. Anyways, 10, 16, 25, that's 35. Hold there, buddy, that's 35. So that means that's, what is it, section 15I? So actual, let's take a look what it says here. Nearest neighbor algorithm gives A, D, E, B, C, A with an actual root of A, D, E, D, B, C, D, A, 39. But I just, it doesn't say start at A, does it? E, D, C, B, A, E. Well, the book is wrong. However, this could be a mistake in the book because all of the answers to all of these problems all start at A, even though it doesn't say anything about requiring you to start at A. But that answers that question. So apparently, You don't always have to start at A, of course, and it does make a difference where you start. One may be better than another. Okay. That being said, now that we've established that, from here on out, to save time and to do it the way the book does, we'll always start at A, even though they didn't specifically say so, just because otherwise it's just very time consuming. So here's A, here's B, here's C, here's D, here's E, here's F, back to A to C, F to C, E to C, and we got weight 6, 3, 7, 4, 5, 6, 8, 5, 7. So let's first make our table. And we're going to have A, B, C, D, E, F 6 points. A, B, C, D, E, and F. A, B, C, D, E, and F. First throw in the zeros. Okay. A to B is clearly 6. And A to F, it's not, it doesn't have to go in order. A to F is clearly 4. A to C is clearly 7. Okay, now A to E is clearly 10. And A to D is not clearly anything. Now we got to look. A to D, I can go this way, that's 17. I can go this way, that's 12. Oh, looks like 12. Yeah, looks like 12. A to D, 12. Meanwhile, B to C, 3. Nothing beats that. B to D is 8. B to E, looks like 11. B to F, 10, 8, looks like 8. C to D, 5. C to E, 8. E to F, 6. D to E, 7. D to F, 10. And E to F, 6. Okay, that's my table of least weights. So now let's find a good path. Starting at A, cross out A, and A goes to F, and that's direct. Cross out F. F goes to either C or E. So we have 2 possibilities here. So let's do C first. If it goes to C, then C then goes to B. B goes to D. And then D goes to E. And then back to A. Let's see if it's direct. A, F, C, B. Nope. In here between B and D, I have to throw in, B, D. I have to throw in a C. And D, E, and then E to A, I got to throw in an F. So that would be that route. Okay, do they want the weights? Yeah, state the total root of the weight. So A to F, 4. F to C is 5. C to B, so it's 4 and 5 is 9. To B is 12. Back to C is 15. To D is 20. To E, 27. And then 37. Of course, that's just the AFC route. The other possibility, or at least another possibility, because maybe there'll be another deviation after the fact. Okay, well, let's take a look. So A to F. A to F was 4. And then we crossed out the rest of F's. And then F to E was 6. Crossed out the rest of the E's. and then E to D, 7, cross out the rest of the D's, and then D to C is 5, cross out the rest of those, and then C to B is 3, cross out the rest of those, and then B goes to A. I forgot to cross out the A's. Or I did, but I erased them, I guess. And that's, okay. So let's take a look. A to F is direct. F to E is direct. E to D is direct. D to C is direct. C to B. Oh, and this one does not require any extra vertices. So AF is 4. D is 10, 17, 22, 25, and this should be 31. So that should be 31. So then it says, if more than one root is possible, give the upper bound for both roots. In other words, we know it's going to be less than 37. That's an upper bound. And we know it's going to be less than 31. That's an upper bound. But unless I made a mistake, 31 is a lot better. A, F, C, B, D, E, A. But what about A, F, E, D, A, F, E, D, C, B, A, 10, 17, 10, 17, 22, 25, 31. Buck is wrong again. The book is wrong again. Oh, unless I am wrong, but I don't think I am. Then again, nobody ever thinks they're wrong until they're proven wrong. 10, 17, 20, 20, 31 looks good. Okay, and then part C. Let's see what we have here. A, B, C, D to C and to A, E to D, and F. And then we have 6, 4, 6, 5, 2, 4, 5, 3, and 4. So we have another 6 points. A, B, C, D, E, F. A, B, C, D, E, and F. So A, B, C, D, E, and F. All right. A to B is clearly 6. A to C is clearly 6. A to D is clearly 5. A to E, 4. And A to F, let's see, that one is 9. 9, it looks like. B to C, 4. B to D, 6. B to E, 9. And B to F, 8. C to D, 2. C to E, 5. C to F, 4. D to E, 3. D to F, 6. And E to F would be 5. Okay. So now that we have the table, I don't need the graph anymore. So let's go. A. And A goes to E. And E goes to D. And D goes to C. And C goes to, oh, now we have 2 choices. C goes to B, or C goes to F. So let's do B first. I'm going to do a different color here, so I only erase this part. If I go to, where am I? If I go to B, and erase those. And then B goes to F, which has to return to A. Oh, so that wasn't a lot, actually. If on the other hand, I keep purple. If on the other hand, I go to F, then if I cross out the F's, F goes to B, which then has to return to A. Okay, so now A to E directly 4, E to D directly 3, D to C directly 2, C to B directly 4, B to F is indirect. I got to throw in a C. Let's see how I do this. I can throw in a C, but overall B to F is 8. And then F to A is 9 if I go through E. So C, E gives me the direct route. For a total of 5. All right, well, sorry I had a phone call. I'm back. I don't remember exactly what I left off at, but it looks like I had just finished this path, which gives us a weight of 4 plus 3 is 7, plus 2 is 9, 4 is 13, 21, that's a weight of 30. So that's an upper bound of 30. And the other one, A to E is 4, E to D is 3, D to C is 2. Now C to F is 4. F to B is 8. Going through C. And then B to A is 6. And this gives us 7, 9, 13, 21. That's an upper bound of 27. So because I got interrupted, I don't remember exactly. Just want to check this. This is in 15I, 1C. Yeah, 30 or 27. So 27 is the better upper bound. Okay. And then we have part D. So here's A, here's B, here's C, here's D, here's E and A. 10, 50. Oh, there's also this one, D to B. It's 15, 15, 20, and 25. So let's make our table of least weights. We have 5 points, A, B, C, D, and E. A, B, C, D, and E. First putting the zeros along the main diagonal. A to B. Aha, A to B, it looks like 50, but it actually can go down and around. A to B is 40, it looks like. 10, 15, 15. A to C, if I go that way, it's 75. If I go 10, 25, 45, it looks like. A to D is certainly 25. And A to E is definitely 10. B to C is 25. B to D is clearly 15. B to E is 30. C to D is 20. C to E is 35. And D to E is 15. Okay, so now, starting at A, if we cross out A's, and if we see A goes to E, and then E goes to D, and then D goes to B, and then B goes to C, which has to then return to A. A to E is 10, E to D is 15, D to B is 15, B to C is 25. And then C to A, I'm going to throw in, we know C to A is 45. But how do I get from C to A the fastest? D and E in between. So I get 10, 15, 25, 35, 40, 85, 90, was it 110? So we see that we have an upper bound of 110. And I think this is why we just call it an upper bound and we don't just say, oh, here's the answer. As we saw in part A, for part A, we actually went through every possible starting vertex and showed that there's actually a better upper bound of 35. So unless we actually go through every starting vertex, we don't know that 110 is the best, the minimum possible weight. Maybe starting at another vertex would be even better. But it looks like we're only starting at vertex A here, even though nowhere in the question does it say that. So that's just a mistake. It should really mention that. All right, question number 2. The following diagrams illustrate why the nearest neighbor algorithm should always be done on a complete graph which satisfies the triangle inequality. In each case, apply the algorithm directly to the graph and comment on your findings. All right, so let's comment on this. We have A, we have B, we have C, and then we have D right in the middle, which connects to D, which connects to A, which connects to B. This is 3, this is 5, this is 4, this is 500, this is 6, and this here is 5. Obviously, 500 is a huge number in comparison to the rest. We know we are certainly going to avoid the AD connection. So this is a complete graph because A connects to B, C, and D, B to A, C, and D, C to A, B, and D, and D to A, B, and C. It's complete, but it does not satisfy the triangle inequality because obviously we can see A to D is not the shortest route from A to D, but rather anything else would be better. So let's take a look at what happens when we apply the, this is much bigger than is needed. Okay, so let's take a look. We have A, B, C, and D, A, B, C, and D. We're going to use the, we're going to make a table of least weights. So A to B, 3, clearly. C to D, not going in order here, but C to D is clearly 4. B to C is clearly 5. B to D, clearly 6. That 6 should be over here. And we're missing A to C, which is clearly 5. Those are all the easy ones. And then there's AD, which is clearly not 500. If we go this way, it's 9. If we go that way, it's 9. So A to D is 9. Okay. It says in each case, apply the algorithm. Okay, well, first it says apply the algorithm directly to the graph. Apply it. So this is what we would do if it was least weights. So let's first do it directly. A. The shortest, well, you know, yeah. So let's do the following. Make this a little clearer. Let's make 2 tables. So let's copy this one, duplicate it, and we'll fix AD to be 500, which is this is the table of weights, and this is a table of least weights. So let's apply it directly. A, cross out A goes to B, cross out B goes to C, cross out C. C goes to D, which then returns to A. Okay, well, that's fine, I guess, I think. A to B is 3. B to C is 5. C to D is 4. And D to A, I mean, if you go by the direct route, it's 500, which would give us 512. If I do it with the least weights, A goes to B, B goes to C, C goes to D, which then goes back to A via the shortest route, A to B, B to C, C to D. And then what's the direct route from B to A? It's 9 via C. And this, of course, gives us 21. So I'm not exactly sure what they're asking for here. It says because it does not follow the triangle inequality, the up or down produced by the NNA is far higher than the solution to the TSP. I mean, that's kind of obvious. I kind of feel that the question was kind of silly because clearly, obviously, well, maybe this is the whole point. 500 is kind of like an exaggeration, but even if it was 20 or 30 and not so much higher, maybe also you'd be more likely to make a mistake, which is why it's so important to make a table of least weights so that we satisfy the triangle inequality and we don't have this issue. This was part A. And then we have part B. So here's again A. These numbers are all reasonable. So let's take a look at what the point of this one is. 4, 4, 3, here's D, here's F, here's E, and that's 3. Okay. So the following okay, so again, let's make 2 tables. Let's start with A, B, C, D, E, F. A, B, C, D, excuse me, F zeros along the main diagonal. A to B is 6. A to C is 4. A to D is also 4. A to E is 10. A to F is 9. B to C is 7. B to D is 10. B to E is 16. B to F is 15. C to D is 3. C to E is 9. C to F is 8. D to E is 6. D to F is 5. And E to F is 3. This is a table of least weights. Now this one is not complete. Oh, maybe that's the issue. Okay. So let's okay. We know there's no issue with least weights. The issue is with the actual weights. So let's fix this and just make it the actual weights itself. If we go A goes to B, goes to C, goes to D, A doesn't connect to E or F. B only goes to A and C. C only goes to A, B, and D. D goes to A, C, but not B. E and F. E goes to D and F. and F goes to D and E. Okay, and so I think this is the issue. What if it's not complete? Well, if we try to use the algorithm here, we start at A, cross out the A's. A goes to C or D, let's say C. Cross out the C's, C goes to D. Cross out the D's, D goes to F. Cross out the F, F goes to E. Cross out the E, and then E's got nowhere to go. Uh-oh, but we never hit B. And that's it. That's why it's bad. So make the table of least weights so we know that we have a complete graph that satisfies the triangle inequality, and then we don't have to worry about it. So this is the first half of 15.5. I'm going to make a second video for the second half because I have to go and do something. So yeah, that's the upper bound half. See you soon for the lower bound half.